Hello everyone, welcome to our second Guide to Galaxy session of this year. So I am Amishi and this is Abhishek, and we both will be taking a session on Asteroseismology. So yeah, again we appreciate your enthusiasm. If you guys have any doubts or something in the middle of the session, please feel free to ask. Also feel free to approach us in the end of the session. And yeah, just to be clear, this session doesn't require some very advanced maths or something. Again, just to throw this out there. This session is supposed to be an introduction to this amazing field that we are going to talk about right now. So, yeah. So now, just to look at this. We can't hear it with our ears, but the stars in the sky are performing a concert, one that never stops. So this is essentially the idea of asteroseismology that we see. The stars over there, if you think of them as some rigid, stationary spheres in the sky, right? In asteroseismology, you do away with this notion completely. Your stars, they aren't spherical anymore, per se. They are oscillating. They are basically the entire surface of the sphere is oscillating. So yeah, their shape is changing a bit. We'll get to that in a bit. We will show you how it changes. So okay, again, now for the stuff that we'll be covering. So in the beginning, we'll just cover some of the basics required. Basics like the structure of the star and what the HR diagram is, etc. Next, we go on to excitation mechanisms, then types of oscillators, conservation laws, the solutions of the wave equation essentially on a sphere, on the surface of a sphere. Then we go off to spherical harmonics, and then we'll also be elaborating about the modes of vibration. We'll also be elaborating on some observations, the luminosity observations that we have obtained, and the formulae required to do so. We'll also be talking about some key space missions and some notable results that they have produced, and ultimately we'll conclude with the future of this field. So again, the principle of asteroseismology. A star is a gaseous sphere. It will oscillate in many different modes when suitably excited. And the perturbation you'd ask, how does it actually get excited? It's all within the star. It's in the inside of the star. Basically, the insides of the star aren't exactly static. So yeah, that is what triggers it. And that is what makes stars oscillate. And also the frequencies that make the star oscillate, right? They depend on multiple factors. Basically, the speed of sound in that star is. And that itself is dependent on many factors which are already listed. Density, temperature, everything. So yeah, again, this field is asteroseismology, and it tells you a lot about the star, from its age to its composition, a lot of things. Now, heading to the basics, the first thing that we'll be covering is the structure of a star. So here you can see this diagram is essentially our dear sun right here. So now I'll just be talking about the regions of our interest. This diagram lists out a lot of regions which we won't really be focusing on in this field. I'll just be talking about the important ones. So this over here is called the convective zone, and this over here is called the radiative zone. For the radiative zone, at least in the sun, it's located towards a little more towards the interior, a little closer to the core as compared to the convective zone, right? The radiative zone, the speciality of this zone is basically that energy, the way it is transferred, it usually travels in this zone through, you guessed it, radiation in the form of photons. And this zone is just so dense that light itself takes millennia to pass through it. So that's the radiative zone. Convective zone, for that matter, it's way less denser as compared to the radiative zone. And again, there are a lot of convection currents in here. You might have already, you might have seen it sometimes. Some cycles in here, like in a diagram of the sun or something. It's not shown over here, but yeah, those are that's the visualization of the convective currents basically. So this zone is essentially it's less dense and it's a bit disturbed. So yeah, again, these are our regions of interest. Okay, you might be wondering what the decocline is. That's nothing, that's just a transition region. Because owing to this density difference and everything, you have a very, very large region of shear that gets created in the star. Okay, so again, as I already said, convective zone. It's unstable due to convection, the currents, and energy, as you can already see from the name, it's transported through convection. And similarly for the radiative zone, I've already elaborated on that. Next up, Abhishek will cover the HR diagrams.
So, what HR diagrams basically are is unlike its name, they are just graphs of some data from the stars. It helps us to categorize and organize the stars better. So let's see an example graph of it. So this is a very rough example of a HR diagram. So what we have on our x-axis is the temperature of the star. Sometimes you will be seeing it with the spectral maximum wavelength of its spectrum, or log of the temperature in a logarithmic scale if they want to show in that scale. And the y-axis is the luminosity. And again, based on the people who are studying it, it varies. Is it compared to sun or some standard star? It keeps varying at the scale and all. So when we plot out the stars in this data frame, we get a particular pattern. So this here is called the main sequence. All the stars which are currently burning hydrogen in them and are in the medium stage of their or early stage of their life lie in this main sequence. So as they approach the end of their lives, so based upon their mass, either they separate from the main sequence and become white dwarfs, or they separate towards the up and they become red giants. So this diagram really helps us to classify the stars. When we find a star, if we calculate the effective temperature and the luminosity, we can kind of classify it if it is a red giant or white dwarf or whatever. So this which you would be using very much in this session, but we'll be looking at some graphs which look similar to this. So it will be better to visualize the stars if you kind of understand. Just remember that the lower ones are white dwarfs, upper one are red giants, in the middle are the normal hydrogen burning stars. So this is another HR diagram again. So everything is same except that we have a classification in here if we see. So these are the types of stars based upon their number. Stars are classified. Why and all we aren't bothered in this session, in this topic. Just remember that there are some classifications for stars, and even upon the reasons here we have 5th type, 6th type, and we have some types. So though we will be talking about some stars in those areas, like kind of an example stars. So that's it. And then we move to somewhat relevant topic, the excitation mechanisms. Like we will be seeing what are the reasons causing these oscillations, or what are the mechanisms these vibrations are getting energy from. One of the major mechanism of vibrations is called the kappa mechanism or the heat engine. It is the most basic mechanism by which you can cause oscillations in stars. So what it basically is like, as you know, based upon the density of a material, its opacity might change, the way it interacts with light, how much light it allows to pass through. So similar way, the convective zone or the surface of a star has its opacity depending on its temperature. So when its opacity is high, it will absorb more of the radiation coming from the inner line, the radiative zone. So it heats up. So while heating up, it kind of ionizes if there are any molecules left over there. It ionizes and its energy increases, so it expands. So the surface expands and effectively the radius of the star increases while we are observing it. So it expands, and while it is expanding, its density will be reducing, obviously, and as it goes further, its opacity will be reducing since its density is reduced. So it won't be able to absorb as much energy as when it was absorbing initially. So it starts to cool down. So while it is cooling down, again the ionized particles all they form molecules and recollapse to its original state. And this goes on like a cycle. When it collapses, it heats again and expands again. So this drives the waves, oscillations, vibrations in some stars. So this is a major mechanism, like the most prominent vibrating stars, like we speak about pulsars. They most prominently use this mechanism for their vibrations. And then we have surface convection. This is the mechanism that happens in our sun. So this basically is like a stochastic mechanism. It depends on the probability of happening. Like in the convection zone, we know the temperature transfer happens through convection. So there will be convection currents, which are basically turbulent movements of the gas to the lower region and then upper region. So these turbulences, since by the name, they won't be very systematic. So these turbulences kind of can create disturbances in the surface in the convective region. So at times when the frequencies are right, these turbulences can travel around the star to form a standing wave or a stable wave. So then these waves kind of survive due to the turbulence in this region, and that is one mechanism. And this happens in our sun. So whenever we speak about surface convection, sometimes people also talk it as solar-like mechanism, or all the stars which have surface convection as their oscillation mechanism are called solar-like stars, which we will be coming back again, the types of oscillators. So and then we have convective blocking. It is similar to surface convection, but some influence to the radiation also. So what basically is like some stars might not some stars when they oscillate due to the kappa mechanism or the Hutchinson mechanism, they also will have a convective zone there. So when these convective currents, if by chance the time period of the convective currents is at a particular scale to the time period of the oscillations caused by the heat mechanism, these convective currents can also provide energy and excite the oscillations caused by the heat mechanism, kappa mechanism. So that time the oscillations will be powered by a kind of combination of the heat engine mechanism and the surface convections. So these are called convective blocking. And then we have tidal excitation. This is the odd one out in all the mechanisms. This is very different because this is caused by the star itself. So we have binary star systems, right? So when they orbit each other, at some point they will be the closest. So when they are the closest, they form tides on each other's surface, like moon forms tides on Earth's surface. They also form tides of the convective zone. And when they are the closest, the tides are at the highest amplitude, and when they are the farthest, the tide is at the lowest point. So when this keeps on repeating, if the time period and frequency allow them to form standing waves, these can form sustaining vibrations in the stars. So this is a different one compared to all others. So these are the four major excitation mechanisms. There are like few minor excitation mechanisms like observed in few stars. So, but these are the main mechanisms. Most of the other mechanisms like would be a combination of these or slight variations of these. And then based on these mechanisms and few more characteristics of the oscillations, we classified the stars into some types of oscillators to call. Amisha will be speaking about those types of oscillators.
I just wanted to give this one thing a mention. Did anyone of you notice the spelling of Asteroseismology? The way we spelled it. It is spelled with an E. Yeah, so see, let me just clarify this before it gets like too late. So Asteroseismology, don't be confused for don't confuse it for a typo or something. It is where should I write? I think I'll just write it over here for the time being. So yeah, so this is how the word is spelled. So basically that is because the root of this word is essentially the word aster, which is Greek for star. Now, astron is also Greek for star, but it wasn't the more popular version. This was the more popular version, actually asteros, so that is how it is derived. This is not a type. Okay, now moving on to the types of oscillators. So first up we have solar-like oscillators. Now these are like excited by surface convection, the mechanism. Our sun is also one of these, and yeah, this is where we have primarily observed such oscillations, hence the name solar-like oscillators. And it's not just the sun. It's like basically all stars which have significant thickness of convection zones, right? They are expected to show such oscillations. So they can even be subgiants and red giants, and not just like main sequence stars like our sun. Okay. Next up, Cepheid variables. So Cepheid variables are an interesting kind of star. They are actually the most important type of oscillator. So these are really heavy stars, as you can already see. Their masses are above about 5 solar masses, and they principally oscillate in their fundamental modes. Now, as far as modes are concerned, whatever oscillations we are talking about essentially manifest themselves as standing waves. So these are the modes in this. Okay. Next up, we have like the time period of these oscillations. They range from days to months. There are a lot of factors over here. There are a lot of variables over here, so that's what it depends on. As far as solar-like oscillators are concerned, I can tell you that our sun, for example, the oscillation period of our sun is like it varies between 2 to 5 minutes. It's rather short. Now, their pulsations, what makes them important is their pulsations are very closely linked to their luminosities. And there are a lot of Cepheid variable stars, which are used as something we call standard candles in cosmology. Now, also if you look back to Hubble's experiment, how many of you over here know about Hubble's experiment? Okay, yeah, can one of you tell me what it is?
So basically measured different star systems, how much redshift and light is.
Right, exactly. So, and the stars that he measured, right? He used Cepheid variables. He looked at those. We have been observing these stars from a very long time. And again, you might have wondered, there was this background video in the contents page. Should I go back? I think I'll go back to it. So, yeah, if you can see this. This is not just a random animation, mind you. This is a very real video. This is the Cepheid variable star RS Purpose in the Milky Way. It is among the brightest stars in this galaxy. Among the brightest Cepheid variables in this galaxy. So, yeah. And now for the Cepheid variables, they are excited by the kappa mechanism. The next category of star that we have are Lyrae variables. These are also very similar to Cepheid variables, and these are also very important. Again, they have also been observed. They are also used as standard candles in cosmology. Now, the thing that differentiates them from the regular Cepheid variables is basically their low mass and their low levels of metallicity. Metallicity being, as you might have learned about it in the previous CQG, basically the content of elements which are not hydrogen or helium. So yeah, that. Now again, these are also excited by the kappa mechanism. Moving on, we have delta sputa. Yeah, carry on.
What do you mean by standard candles? Like the Hubble experiment?
Yeah, okay. So the term standard candle essentially, like, it refers to, it's basically a star, a celestial object with a known magnitude, with a known luminosity. Sorry. Yeah. So once you know that luminosity, you have formulas for calculating the luminosity distance. Now, there is a difference between the concepts of brightness and luminosity. If you look at brightness, what is brightness? In essence, brightness is something, it refers to the amount of light that reaches your eyes. Luminosity is the actual amount of light that is emitted. So, yeah, a standard candle is a measure of that. Now, once you know the luminosity of a star, Cepheid variables, courtesy their very regular oscillation periods, you can ascertain their luminosities very easily. So, hence you use these things as reference points in your measurements of other star systems and stuff. Does that answer your question?
Yeah.
Great. So, okay, next up we have delta square variables. So, these are typically typically A to early F type of stars. I'll show it to you on the HR diagram again, don't worry about it. And then the oscillation periods, as you can already see, range from 0.25 to 8 hours, so relatively short. Cepheid variables in the order of days to months, and these in the order of hours, right? Again, this one is also excited by the kappa mechanism. Now we have gamma Doradus stars, which are, for a change, excited by convective blocking. So these are also these occur towards one end of the delta square variables. Now these, the oscillations that are exhibited in these star systems, in these stars, are usually high order gravity modes. We'll get to that as well. Next up, we have rapidly oscillating AP stars. These are essentially stars of the A type. So again, their parameters overall are roughly similar to the delta square variables. But then we have a very significant distinguishing factor here from other mechanisms. These stars have very strong levels of magnetization. Just because of this, as you might have already known, the Earth has if you look at it from the axis of rotation and the magnetic axis of the Earth, right? We have our Earth's north pole with respect to the axis of rotation. That north pole does not coincide with your magnetic north now, does it? Yeah. So we have it inclined in different directions. This direction is very emphasized in such stars. So this results in very high oscillations. We have very high frequency oscillations. We have it in the order of 1,500 hertz, microhertz. Sorry. So yeah, this is pretty high, and the amplitude difference also is pretty high. Next, we have slowly pulsating D stars. These stars, slowly pulsating, yes, they also rotate very slowly. These are also excited by the kappa mechanism, and basically they exhibit higher order gravity modes. Okay. Beta Cepheid variables, roughly similar to the previous type, slightly hotter and a little more massive. Go see the HR diagram. Again, you only have low order gravity modes. Now we have variable subgroup of D stars. As the name suggests, these belong to the B type stars. These are also excited by the kappa mechanism, and they contain low order pressure modes. short. Now we have white dwarfs. The way we classify them is a bit different. They are classified into three subtypes essentially. So there is DO, DA, and DE. So all of them pulsate. All the three types pulsate, and they pulsate using low degree, high order G modes, gravity modes. So wait. So okay. Now coming to this. This is actually a simulation developed by the ESA. So this one is a Cepheid variable. So as you might see, it's expanding. Okay, the difference isn't as pronounced in reality as it is over here, but you can already see it. These are the kind of pulsations that you can see in these cells. Okay, now on the HR diagram, as you can see all the types that have been discussed here. This over here, this type is the RR Lyrae stars. This is Delta Scuti. These are rapidly oscillating stars. These are the white dwarfs. This HR diagram extends a bit further than like what we have shown you earlier, because it also includes some like theoretical extension as well. So yeah, that's about it. Next, over to Abhishek.
Now we'll look at some mathematical expressions regarding these vibrations, stellar vibrations. So to have a start, like we have some conservation laws which we know, but like we don't know in the form which are useful for stellar calculations. We might not know. So this differential equation that you see here is fundamentally the conservation of mass equation. So, but it is in a differential form, like per unit volume, or when we take a small volumetric region. So it is that. So this differential of density signifies the change in mass in a very differential volume. So that should be equal to the amount of mass that has flown through the region, right? So density into velocity, the differential vector differential basically calculates the entire flow through the surface, a differential surface. So that is the conservation of mass in differential form. And we have conservation of linear momentum in differential form again. So change in momentum per unit volume. So we have density equals to all the forces, like this is the gravity force. G is a function of radius, like G is in the fixed constant. So upon the location of your calculation, that is the G. And F further is like the other forces, like magnetic force due to the magnetic field of the star, or if it is a binary star, force due to the other star. The force per unit volume. Yeah, it is. So the del P term actually is like variation of del. Yeah. Partial derivative of. I mean, like for the conservation of mass, we are bothered with the variation in time itself. Like we don't really bother about the how the density is distributed in the star. We just bother with the fact that in a region, the whatever the mass is changing, that has to leave the surface of it. So we aren't bothered with the distribution of the density. So we don't. Really matter if it is a partial differential or a normal differential. Then we have energy conservation. This basically is the first law of thermodynamics. Change in heat in the system should be equals to change in internal energy plus the work done. So using these conservation laws, what physicists and mathematicians did is that initially using these conservation laws, and we know that star is stable. They formed an equation for the star, how stable it is, any equation they have formed. And after they have formed the equation, they did something called a perturbative analysis. What that basically is like, they analyze how equations or functions behave when their variables are slightly changed. So after doing this perturbative analysis, which on itself is a separate analytical field, which we can't discuss in the scope of this session. So we have got an equation which is, after assuming that the star is a sphere, we temporarily neglected the differences in the star's surface, whatever it is. So we assume that star is a sphere, and they arrived at this equation. So this equation might look large, but you will be using this equation very much. But just let's just take a look at what all the terms are. So this delta r is the radial amplitude as a function of the radial position. This is the angular amplitude as a function of radius again. And this y lm is the spherical harmonic term, which is a standard equation of waves on a sphere. If you it is the eigenfunction on a sphere when you have some particular potential. Like the same term you would have seen in the equation of orbitals if you have studied quantum chemistry. So that basically defines how waves can exist on a sphere, even if you have studied quantum chemistry. That's basically it. So that denotes the radial oscillation term, and this is the angular oscillation term with theta and phi. So and then for the whole equation we'll take the real part, because of the calculation we have included the imaginary numbers also for better calculation of the trigonometric equations. So then we take the real part of all this equation, and you get the displacement of any region in polar coordinates and time. Yeah, these are the different terms in the equation we have there. So we just take a look at different spherical harmonics. Same like orbitals in an atom, we also have quantum numbers. Based upon the quantum number, the appearance, the look, and the shape of the wave keeps changing. Here are some examples, and for better understanding, we'll have. So this, you see, is how the wave looks. It is like a representation, animation. It's not like that. Definitely, the star won't be vibrating in this much amplitude, like comparable to the star itself. It is just an representation, so that we will understand. So yeah, those are the modes in L equals to 1 with m minus 1, 0 and plus 1. And then these are the two modes of spherical harmonics, and just to show you how they look as we increase L value. So here we are only representing L and M because of what they signify. Basically, the quantum number n in the domain of stellar oscillations is the number of radial nodes in the oscillation. So since they are inside the surface, we aren't really bothered by that, unless we have some very specific calculation or some very specific observation we need to find about. So we won't be speaking about the n quantum number very much. So we will be dealing with L and M quantum numbers. The quantum number L basically denotes the number of nodal planes on the surface. Like if we take the example of some one spherical harmonic, here you see in L equals to 1 we only have one nodal plane rotating on the surface. So that denotes the L value denotes those. In L equals to 2 we have two nodal planes which intersect each other. So that is L, and M signifies the number of nodal planes which pass through the rotation axis. So when M equals to 0, the nodal plane doesn't pass through the rotational axis, as you can see, and when M is 1 or minus 1, one nodal plane passes through the rotation axis. the equation of the oscillations, and based upon the frequencies and where these waves propagate, like whether it is a conductive zone or radiative zone, and since their oscillation medium is different, they behave differently, and we will have various modes of oscillation. Amish will be speaking about the modes of oscillations in detail.
Okay, so now we come to the modes of oscillation. Abhishek has already explained to you whatever the significance of the various quantum numbers are over here. So yeah, let's get to it. Before we start this part, before we start the main thing about this part, let me just again show you this image. Again, radiative zone is over here, convective zone is over here. Now, why I'm showing you this is because there are different modes of oscillation and they propagate in different zones. That's the reason why. So again, coming to modes of vibration. Now, we have majorly three modes of vibration. We have P modes, G modes, and something called mixed modes. Now, P modes are also called pressure modes or acoustic modes. G modes are also called gravity modes. Okay, getting to that. P modes. Again, as I already mentioned, they're also known as acoustic modes. They are primarily found in the convective zone. You won't find it in the radiative zone. The main restoring force of such oscillations is the pressure gradient, essentially. And yeah, that is what mediates them. Next up, we have the G modes. G modes, also called gravity modes, they are only found in the radiative zone. Now, you might feel, okay, since the radiative zone, like it's in the interior of the star, these oscillations, like logically speaking, these should progress to the convective zone, right? But the problem is, all thanks to this, like the stability difference inside these two zones, right? As I've already mentioned, the convective zone is essentially very disturbed as compared to the radiative zone. Owing to all the convection currents going on there. Hence, these disturbances dampen the G mode oscillations to such an extent that they die out like very quickly. So, hence, even if they get to the surface, you observe them with very low amplitudes. So, like these are very difficult to observe, especially in stars like our sun. These are very difficult to observe. Now, these are maintained like the overall restoring force in this context is 1. So that's it for the G modes. Now we have mixed modes. So mixed modes, they share the features of both P and G modes. They are sustained both by pressure as well as buoyancy. These two factors contribute, like both of these factors contribute to maintaining. And so that is why they are like sensitive to both regions of the star, both the radiative as well as the convective region. Now, these are actually very important in such terms. In solar-like oscillators, you'll find a lot of these being exhibited. So they actually carry information from deep inside the star, even beyond the convective zone, even into the radiative zone. It just carries all sorts of information about it. So yeah, this is what makes them so important. So here is another diagram of the structure of a star with these modes visualized. So again, this area, this is your pole, this area is the radiative zone, and this is the convective zone, basically. So G modes, they tend to look like this. They kind of propagate in this fashion. They like circle around, they go this way. The moment they hit the convective zone, they hit the tachocline, they'll just bounce back. Similarly, these are the P modes. Now they propagate in this way essentially, in multiple modes. Now, yeah, this is a better visualization right here. All these lines bouncing off from the surface that you can see over here, right? These are all P modes. And this kind of all of these waves that are actually forming some kind of rosette over here, this is nothing but the G modes. Yeah, mixed modes are not shown over here, but yeah, you get the point. Here's also here's an animation also. Now this one exclusively shows you the P modes. So again, this is how they propagate. session is meant to be introductory. That is a bit of high level stuff, so yeah, we won't get into that. So once you vary, say, the frequencies, and once you vary the L value and everything, you get all of these. You get these distinct functions. So these functions over here, the ones that take these shape, you'll see these are the G modes. There are also something called the F modes, which aren't really observed. It's purely mathematical actually, kind of.
So the animation that you showed,
Yes.
how exactly do they validate that this is like the P modes and the G modes, this is exactly how they like propagate? How do you validate that in real life from a star? Because all these things is like
Yeah, I understand. So essentially what you see in a star, as Abhishek has already shown you, the visualizations in terms of spherical harmonics and stuff, the net picture that you see, right, it's essentially a sum total of all the things. It's a mix of everything. So, okay, the moment you get something, you observe something, you essentially you observe the variation in luminosities of the star. So, you interpret that, you separate out the frequencies and everything, and then it just goes into some mathematical analysis as well. Then ultimately the resulting things that you get from it, right? This is what it ends up. So these are the functions that you ultimately obtain. These functions, and once you just do some other analysis on it, right? Then you get how they propagate. So yeah, this is how they essentially address this. Does that answer this? So okay, that's about it for the functional part. Now after this, Abhishek will be here to elaborate on some observations and some missions as well.
So re-addressing your question, how we will be validating these oscillations. So this is the technique which we use to observe and learn about these oscillations, the luminosity observations. Since you might know or may not, whatever be the strength of power of a telescope you use, unless it is like extremely powerful, star will still look like a dot through the telescope field. So you can't really observe the localized amplitudes and decide which harmonic it is in. Or even if you could have some very large telescopes and observe these local amplitudes, there will be a superposition of all the harmonics in which it oscillates. So that isn't a very ideal technique to analyze this. So we use something which we readily have, some data which we readily have about a star, and we analyze its vibrations. So what is the most ready data about a star? Very easy to measure. What? Yeah, brightness or luminosity. So we just record the luminosity of star in somewhat great precision. So this is some data from the sun. So you can see the scale of the trend. It is our view of ours itself. So we can see the oscillation in the luminosity of the sun. Not really regular, but you can see the oscillations, right? So we will be analyzing this data. And again, this oscillation is a superposition of all those harmonics, right? So we need to separate those harmonics to study anything about the composition or the structure of sun or anything. So we will be using a technique called Fourier transformation. Have anyone of you heard about it? Yeah. So what Fourier transformation is basically is like there is something called a Fourier series. What it says is that any mathematical function you can write it as the summation of possibly infinite trigonometric terms. So what Fourier transformation does is that it separates out all these trigonometric terms or the amplitude of these trigonometric terms. So when you do the transformation, you will get another function which is the function of amplitude of a certain frequency. Yeah. Yeah, when you separate out it, you get the function of frequency and the amplitude in which it oscillates at that frequency. So as we can see, it really isn't very distinct. Of course, there are some frequencies which have very high power, but theoretically, since the vibrations are standing waves, you should have very discrete frequencies, right? But why are they, although very small, these terms in middle? Can anyone take a guess? Okay, it can be noise, but if you see here, the amplitude of these standing wave frequencies are very comparable to this. Is noise that prominent? And mind it that like all these luminosity observations are not exactly those 4 hours. As you look at it, averaged over a long time, like sets of 4 hours, 4 hours, 4 hours, 4 hours. You take that observation for like a year or something, and then you average it. So noise wouldn't be very prominent. There will be noise. I don't disagree with it. There will be noise, but it won't be this prominent. So what basically is like in the mathematical analysis, we assume that star is uniform, star is spherical, and all this. We took these assumptions, right? But it isn't exactly that way. And we have some magnetic fields also. So at some regions, the composition might be different from the entire star as an average. So in these regions, some frequencies might survive as standard waves. So since there are some regions, some smaller regions, they will have a smaller amplitude. So through not only this specifically, but like whatever be the frequencies we get mathematically, or whatever be the data we get mathematically, it will be different from this. So through the difference, we analyze the stars or whatever there is. So there are basically 2 major parameters that we use to analyze the stars, or better say 3. One is a large frequency separation, which is like if you observe the frequency distribution, the peaks appear to be almost evenly spaced, right? So that even spacing, if you so the number on these peaks is essentially the L value of those modes mathematically derived. So the difference in frequency between 2 consecutive modes of same L value, they define something as the large difference in peaks. They didn't give a name specifically, they just call it large difference or big difference. So that is one parameter. And the other parameter is the difference in frequency of the consecutive L values, different L values. Yeah. Or consecutive peaks. And there is one more thing called as max frequency, at which the power of the vibrations or the energy present in that frequency of vibrations is maximum. So these 3 are the major parameters which we will be using to analyze the stars, which not we. The physicists will be using to analyze the stars. Sorry? That we didn't really find proper way. Like these aren't like direct from any paper or anything. We took these graphs. So these have been used in previous lectures or from in some other universities. Through those YouTube videos, we gathered these graphs. So we don't really know why they use those units. Not as far as we know. Like when studying any large scale observations happening, people tend to change the scale or change the parameter, how they observe a parameter basically. It's like luminosity, its unit should be some cadence or something, right? But whenever we observe the stars, we won't have any units for luminosity. Why? Because we take it related to a star. So the same way, based upon the parameter which they want to observe, they might customize the value which they are looking at, which they graph over. So these are the mathematical equations of those. So the small separation, it doesn't have an exact mathematical equation per se, but we know that it depends upon the metallicity and the age of the star. So that by comparing the small separation to the stars whose age and composition we know, they try to estimate the age and composition of the observed star. But the large frequency difference and the maximum frequency, we have mathematical equations, which again are derived from the initial mathematical equation. So they are prone to error slightly, and we use these formulas basically to find out various characteristics of stars like mass or its radius or something like that. So here on the not mentioned, this is the speed of sound at the particular radial distance. It is c of r. We clearly have to write. So so if you do this, there is an inverse missing. There will be a power -1 here for the delta of mu. Yeah. So if you do that integration again, assuming star is homogeneous, an ideal star, an ideal gas equations, you will get that this integral, including the inverse, turns out to be proportional to the square root of average density of the star. So that is one more thing. And you can also try it out. It isn't much of an integration. Like speed of sound is we have the formula like root or gamma into p by rho. And from these proportionalities, we have something called scaling relations or scaling formula. What we basically do is like we measure those delta nu and nu max values of a particular star, and then we take the proportionality with our sun. So we have these four equations. So if you can measure the frequency separation and max frequency of a star, by comparing it to the sun, we can find its mass, radius, and all gravity at surface or its density.
Here, so data is what is observed through experiments, right?
Yeah.
And we use that data to compute that relation, the radius of the star
Yeah.
or some relation. Usually Vmax is observed from experiments.
Yeah. It is.
And then you try to compute what is the mass of the star or something.
Yes.
You try to account.
Yeah. Again, ending your question itself, since those formulas are from mathematical equations, they are prone to a slight error. But over the course of the large astronomical data we have, also we have some few more techniques to observe these properties of stars, not only asteroseismology. By comparing the result from various techniques, so they have found out that those errors are very small. The scale of astronomical observations, they are very small. We can try out this also if you want. The mathematical derivation of this wouldn't take much time. Let's do it. Just a small time. Yeah, we have these equations, right? Basically, that can be equals to integral of 0 to r of b r by c whole inverse. So speed of sound at any radial distance can be given by our average molar mass by the radius of at that distance. This can be derived like so. General speed of sound in an ideal gas is root over t by mu. We might know it like the ideal gas speed of sound. So from this we can derive this equation, and once we put this in here, we can get it. proportionality, we can remove all the constants. Like m is the average molar mass, right? So yeah, we remove it. It's just root of r. Yeah, wait. Yeah, m is a sorry, m is not the average molar mass, it's the mass of sun. Again, if we do this, we can get. So, removing it out, remove them, and integrating this, we will get proportional to root m integral of. So, root r integral turns out to be r cos 3 by 2 from 0 to r whole inverse. So this is if we take the square root common. That will be directly proportional to root over r cubed by m whole inverse. This inverting is definitely m by r cubed. Since we know m by r cube is proportional to the density, which is m by 4 by 3 by r cube, so we will say it is proportional to the root of density, average density. So and then it's just solving proportionalities, you get these scaling relations. And then we have some space missions which have collected all these astroseismic data. So we have two major space missions, which is Corot and Kepler. So if we see before 2009, before the launch of Corot space telescope, we have very few astroseismic observations of stars. All these dots are the astroseismic observations we have from the terrestrial telescopes. And then we launched Corot, and it gave us some more data, mainly about the red giants and all. So if we see it is like very high increase in number of observations. And then we launched Kepler, which is again very high number of observations when compared to previous. So all this data allowed us to evaluate the properties of various stars and calibrate our mathematical formulas also. We also calibrated the errors in our mathematical formula, and yeah, these data helped us to make many observations. We will see two of those observations. So we could find some helium burning red giants with these observations. What basically helium burning red giants are like when these satellites or these space telescopes were observing some red giants, they gave this kind of a data. This is a red. The top one is a red giant, which we had some data from before also, and also from the telescope we got this data. And this is another red giant. So if we compare this, so here if you see this mode, here L equals to one has a distinct peak and there is some smaller peak of different time value. The difference in frequency is very high. But here we have two peaks at L equals to 1. So how is that possible? Like L equals to 1 should have a distinct frequency. If there are some errors, there should be a small distribution of frequency, right? Why are there two peaks with nearly exact time? So this is because of the mixer modes which we have discussed earlier. Yeah. So mixer modes, as you know, their restoring force is both the pressure difference and buoyancy. So we know buoyancy is in the radiative inner zones where the material is very dense, and pressure variation or acoustic zones are not really stable as far as we have seen till now. But obviously it's possible, especially in red giants. So as you know, red giants is like the core is very collapsed, almost collapsed, and all the outer surface is exploded out and it expanded very much. So why are there acoustic waves or P mode waves, P mode pressure variations in the inner core? So that is explained by one mechanism, which is that these red giants are burning the helium which is left over in their core after the nuclear fusion of hydrogen and helium. So they are fusing these helium again. So when they are fusing again, we get some heat and it creates some turbulences. So we can get something similar to a convective zone in these cores. So like it is less denser than a regular core. So there can be pressure difference and pressure waves can exist. So we will have some mixed modes there, which is why at one L value we are having multiple peaks, 2 peaks. So we have observed such helium burning red giants very much through these telescope observations, space telescopes. And another observation which is more fascinating than the other is Kepler 56. It is a star. So from previous observations, we got to know that there are 2 planets around this star, and the orbiting plane of these stars, of these planets, aligns with the line of view of the star. Oh, that is very nice. And then when we are observing at various frequencies, at one particular L value, the 3m values have very comparable frequency amplitudes. Generally, what is like you see when m equals to 0, the spherical harmonics are symmetric about the radial axis. If someone has noticed that in the spherical harmonics, or will go back. So due to this symmetry, these frequencies are very stable and they tend to have higher amplitudes when compared to the other m values. Even in the other m values, based upon the direction of rotation of the star, various m values have varying stabilities and varying amplitudes of their frequencies. But why are all the 3 m values very close in amplitudes? Or at least as we observe, they are very close in amplitude. So why this is? So one explanation, like the explanation for this is that suppose the star is spinning about an axis which is perpendicular to our line of view. So what basically is this keeps rotating, and once you get a region which oscillates, keeps oscillating, so there will be some variation in the luminosity you will observe. And when it completes a rotation, the opposite phase you will be seeing, and you will see some oscillation. So you will be having some amplitude of vibration. And when there is this normal plane towards you, you will not see any variation in luminance. And for m equals to 0, since it is symmetric, you will see half region in in one phase and the other half in exactly opposite phase. So how long ever you see, you shouldn't see any vibration in this frequency, any luminosity difference in that frequency. Similarly, if the rotation axis is parallel to our line of view, for L equals to 0, you will continuously be seeing one specific region which oscillates. So you will be seeing some amplitude in luminosity variations. And the other two kind of become like the m equals to 0 in our previous orientation. You will have half of those regions and you shouldn't be seeing any variation of luminosity in that frequency. But we are seeing variation in all the three m values and the same frequency. So the explanation is that the spin axis is at a 45-degree inclination from our line of view. So now it is similar. See here the red area, like the red and blue are just symbolization of phase. The region which is in red and the region in blue are exactly opposite in phase. That's it. So in this we have a region with red value, red phase very much, and very small region with blue phase. So we will see some variation in luminance, and that will be at some amplitude. So and in this we have blue region very large and the red region very low. We will see similar amplitude again. Same here also. So due to this orientation, when we are observing, we are seeing almost equal variation in luminance. Where that is where it is. We have 45-degree inclination, but it is created one more problem. So like whenever we observe the planets, either planets around the sun or planets around some other stars, what happens is like the spin axis is not very much inclined to the orbital plane. Like it is close to perpendicular. but 0.5 degrees is very high inclination. We have seen some stars, but all those stars have one single planet. We never seen this much inclination in multi-planet stars. So, like generally, how do planets form? Like the most prominent theory, like when some mass gets exploded from the star, it keeps oscillating, it gets trapped in gravity. So, theoretically, due to conservation of angular momentum, it should be very close to the same axis of rotation, right? It shouldn't be very much inclination. So, what they kind of proposed or postulated is that we have seen two planets, it is fine. There should be a third planet or more than three, might be possibly. So that when you take a net angular momentum of all those planets, or at least three planets, the angular momentum isn't very much inclined with the star, the net angular momentum of the planets. So they postulated that. After a few years, due to few more observations, they have finally found the third planet also. So basically, like astroseismology is the most prominent use is this only. We will be analyzing the stars so that we can know the properties of its exoplanets. So, like since the exoplanets are very far, what are the properties of the exoplanet, like the radius or mass? You can only calculate them as compared to its host star, its ratio. So through astroseismology, you calculate the properties of the star, and then you can know the radius or mass or whatever of the exoplanets. This is a major use of astroseismology, and there are many more observations and predictions that have happened due to astroseismology, but these are two major ones. The other ones, and then this session is coming to an end, and what are going to happen in the future of astroseismology. Amishi will be speaking about this.
So now Abhishek has already explained a lot about basically like two of the missions in particular. We have Corot and Kepler, as well as the very significant observations that we have seen. So adding on to that, the future of astroseismology, what it holds. First up, this is the TESS mission, short for Transiting Exoplanet Survey Satellite. So this is already in orbit currently. It's not a future mission or something, but it's not even decommissioned or something. So this has already increased the number of our observations by a very significant amount. So okay, this is one thing. Another one of such missions is the Plato mission. Now this one will be launched in 2026. So we expect this one to further expand it by to maybe more orders of magnitude maybe. Okay, now we're done with missions. Now again, about basically what astroseismology is. Astroseismology in essence is nothing but a way, a technique of characterizing stars, right? So now another implication of this is, this in theory can be used to contribute to the detection of dark matter. How, you may ask? So if we observe some stars, if we observe their oscillations and everything, we can definitely make some predictions if they are regular enough, right? So okay, after isolating whatever modes of oscillation, whatever specifics we have, even then, if there is some significant amount of difference, I won't call it an error. There is another way we can explain it. We can think of it in terms of dark matter inside the stars. Inside the stars, like the dark matter in question, the particles that I am talking about are axions. So if we see such a significant deviation from our projected data and between our projected data and our observed data, and if the explanation comes out to this, that's it, we've solved dark matter. So okay, this is how you can actually predict this kind of stuff using astroseismology. Again, hypothetical, but possible. Yeah. So now, next up we have the significance of astroseismology in the field of galactic archaeology. Now, okay, too many terms, I know it's a mouthful, but galactic archaeology is basically how, like, you can explain the evolution from the start to the current, to the present times to the future of how a galaxy is progressing, right? So that field, the field where we study all of this is galactic archaeology. So just by characterizing stars using astroseismology techniques, this has contributed very significantly to this field, and it will continue to keep contributing to this. Now, this over here, as you can see, this diagram over here is nothing but like the parts of a galaxy that are considered in the field of galactic archaeology. So again, this is the this over here. This is the bulge of a galaxy. These are all different regions of stars, essentially. I wouldn't go into detail in this again, but yeah, by characterizing the stars in all of these regions, you can understand the journey of the galaxy through time. So these are just some of the many extremely large number of future applications that astroseismology may have. So that's about it from our side. Thanks a lot. We hope this session enjoyed.